Okay, now we will look at one-way ANOVAs specifically, and again, just covering the most important things you need to know about one-way ANOVAs. So when we say one-way, that just means there is one factor, i.e. one independent variable. The key thing again is that we're going to be dealing with three groups or three levels of that independent variable. So some things to look out for is just make sure that when you read a word problem, you can understand how many levels of the independent variable there are. Just some examples of what a one-way ANOVA might look like as far as the groups or the levels it would include. You might look at an independent variable that is treatment group. There are three levels: no treatment, some old treatment, some new treatment, drug groups, placebo, drug 1, drug 2, maybe even a course section like one class, but there are three sections: class 1, class 2, class 3. These are all things that would fall under having three levels of that one independent variable. Now, you notice that I just directly skipped any hand calculations to go straight to this ANOVA table. That might be indicative of what you would actually be asked to do on the test. That is, if I don't show you how to do some of these hand calculations, maybe you won't have to do a lot of hand calculations on the test. However, I want to talk about the important parts, so I went straight to this ANOVA table. So that might be a hint. So if we look at this table, I have just filled in the components that make up the parts of this ANOVA table. So you have seen this hopefully within the lecture, within the book, and pretty extensively within the lab. So just go over some details that we see in these things. One of the important things, we talked about how variance is broken down to a between groups component and a within groups component. You're going to see some terms used interchangeably, whether you're talking about the lecture, the book, or say for the lab, because SPSS has its own way of outputting these things. So whenever you see group as the variance source, that's the exact same thing as between. So sums of squares or degrees of freedom for the group is the same thing as for between. Group is referring to between groups variability. Within groups variability, you will also see that as error. With error for sums of squares error, degrees of freedom error, again, all used interchangeably. Make sure that doesn't throw you off. When you see within, it's the same thing as error. When you see between, it's the same thing as group. You're going to see both of those terms. I stress that. So don't get confused over which is which. So the whole thing we need to do is use this table to get to the F value. And it turns out it all builds on itself, but we're going to work backwards. So we get F by comparing or dividing the means to square group, or again, mean square, that's what MS stands for, mean squares. Mean square between divided by the mean square error, aka mean square within. This is a ratio. Again, the F value just represents a ratio between two variances. So to get to those mean square values, you treat them the same. So to get the mean square group or mean square between, you just take the sums of square group divided by the degrees of freedom group. You do the same thing for the error component of variance. You take the sums of squares divided by degrees of freedom. That's going to hold true for everything we do. And even though you might think I don't actually know how to calculate mean squares, you have been doing this quite a bit up to this point, hopefully, actually. You think about another situation where you've taken some sum of squares and then divided it by the degrees of freedom. Well, that's all we did when we were doing the variance and standard deviation, where you get the variance, then you take the square root, and that's the standard deviation. But up to that point, if you can recall the formula for variance, the old formula here, that is the same thing as sums of squares divided by degrees of freedom. So that's practically the same thing as mean square there. So even though you will not necessarily be making that calculation, you've been doing this. So we're just actually partitioning it. So again, mean square is just the variance for the between groups, or It's going to, again, show up as sums of squares between or sums of squares group, doesn't matter. And the variance for within groups or error. So F is just a representative ratio for those two variances. So there are some important properties of this F table, or the ANOVA table. So we see we have group, error, and total, but total wasn't actually used when you calculated F. So what's the point of having this little row in the table for total? It's because it's so useful, because you only need 2 out of these 3 things to calculate the other. And that's a pretty important part of the ANOVA table. Group plus error is going to equal your total. This holds true for the degrees of freedom and for the sums of square. So if I have 2 out of the 3 here, I can easily calculate the other. So for example, I do not know what my degrees of freedom is for the group partition of variance, or the between groups variance. However, keeping in mind those properties, the fact that group plus error equals total, I can rearrange that and say that if I take total minus error, I can get my group property. And this holds true whether we're talking about degrees of freedom or sums of squares. So here, I know that the total is 7, the error is 5 for the degrees of freedom. Then for the group degrees of freedom, I know that it is 2. So that's a pretty valuable property. It's really useful because if we were to actually have to hand calculate this whole table, if you were just given 3 groups and the values for all 3 groups and you had to calculate it from scratch, which you will not have to do, you would actually only need to calculate 2 out of these 3 things and then use those properties to come up with the third. Now the reason why that is useful is because most of the time when you can avoid it, you don't want to hand calculate any of these error terms. Especially sums of square error. That one's the most tedious out of all these cells in the table. That one's the most tedious to calculate. So if you did have to hand calculate it, everyone pretty much chooses to hand calculate sums of squares total and sums of squares group, and then use those properties to then fill in sums of square error. So it's a time-saving measure. But again, understand those properties, but understand you won't have to hand calculate an ANOVA from scratch. So let's try an example here where we just have the table, and let's look at those table properties and how they work. So let me come up with a different pen color here. So I still have everything I need to calculate F. I don't have a whole lot here, but it is plenty. I know that sums of squares total is simply going to be, or not total, but the sums of squares group is simply going to be total minus error. So 300 minus 25 should give me 275. Okay, the same thing for the degrees of freedom. So now that I have, all I need is sums of squares and the degrees of freedom, and everything else I can start filling in. So to get mean square here, again, it's just the sums of squares divided by the degrees of freedom for this row. So 275 divided by 3, 91.67. Same down here. I get them from over here. So F is just mean square group divided by mean square error. That would give us 25.68, if I did that correctly. So now we need to compare that to some value, some critical value for f. There's two things I need to know. We notice that there are two columns here, something for the numerator and then something here for the denominator. So what is the degrees of freedom for the numerator and degrees of freedom for the denominator? So the numerator is simply the, for that group row or that between row, the degrees of freedom for that. The denominator is the degrees of freedom for the error variance or the within groups variance. So looking back here, that means 3 and 7, numerator and denominator. So did some I got my calculations off there. Go by these values here, not what I have afterwards. So what were our degrees of freedom here? 3 and 7, 3, 7. So our critical value for f is 4.35. And looking back, we far surpassed that. So let's do a tougher example here, and then we'll talk about actually how to write out those results. So I still have everything I need. The example here says a researcher divided 40 participants into 3 groups. It really doesn't matter what those 3 groups are. Let's just say placebo, drug A, drug B. And we only have one column here filled out, and that's the sums of squares. You notice we don't have degrees of freedom filled out, or even the anything else beyond that. All we have are the sums of squares. We still have all we need to complete the table. And that's because it is pretty easy to calculate the degrees of freedom for these things given the information up above. So we have a couple of important numbers here, 40 and 3. And as long as we have those numbers, we can calculate the degrees of freedom for the total column or the total row and the degrees of freedom for the group row. So if we have 3 groups, and degrees of freedom from the groups is the number of groups minus 1, so that is simply 3 minus 1, or 2. And again, error, pretty much everything for error is more complicated. It's not impossible, not really that difficult, but we'll go the easier route when we can. So instead of calculating degrees of freedom for the error, it's recommended that we just do degrees of freedom for the total, which is something we're really used to. It's just the total n minus 1. So if we have 40 participants, that's 40 minus 1, simply 39. So again, using that property of degrees of freedom error, meaning df total minus df group, then I know that this is 37. So that's just simply 39 minus 2. So then here, again, it's the sums of squares divided by the degrees of freedom, which is 250 divided by 2, which gives us 125. Same thing here. So 25 divided by 37, which gives us 0.68. So then we know f is simply mean square group divided by mean square error. If you do 125 divided by 0.68, you get a large number here, about 183.8. So again, we want to go to our critical value table, that table E3. And just ahead of time, we should go ahead and know it's going to want the numerator and denominator, degrees of freedom, numerator, denominator. We're looking for 2 and 37. So 2 and 37 is way on down the page, but just know ahead of time that it is less than 0.05. You will not have one like that on the exam, of course. And how do we write this up? So it's a formula essentially of df numerator, df denom. So these are the same two values you used in finding the critical value, equals the actual f value, and then p. So to write up this result, 2, 37, and so where did I get those things? And again, this is based off of the critical value that we compared it to, which anytime you have a value this high, you're pretty much going to be rejecting the null hypothesis. You're going to find that rejection region. You will not have to look up one that large, of course, on the exam. So the bottom line here, the take home, is that if we do find a significant ANOVA, like in that example, really both examples we just did, it tells us if there's a difference among the three groups. There is some difference among some of these groups. The problem is we don't know where. We only know if. So if we have three groups that got three drugs, placebo, drug 1, drug 2, we had recorded their anxiety symptoms after these drugs, and then we ran a one-way ANOVA. That independent variable or that factor would be drug group. The levels would be placebo, drug 1, drug 2. Significant ANOVA or F-test would say that, hey, there is a difference among in the anxiety symptoms among these three groups. Between which groups, we don't know. We just know it's somewhere among these three groups. Could be that there's a big difference between drug 2 and drug 1, or it could be between placebo and drug 1. A lot of possibilities, but the fact is we don't know where that difference is. And that's where the next thing comes into play.